All right, I'd like to introduce our speaker, Peter, who's developing on libusb. And this is a talk I was interested in because I am an embedded systems developer, and for many years I would get these little Linux boards that just have a TX, RX, ground, plain old serial, and I wire it to my laptop, and everything works fine. And now my last fucking 3 laptops don't have a goddamn serial port, and I have to get a goddamn FTDI chip and hope that the driver works for it, but there must be some great reason for why we have this now, and maybe Peter can explain to us what it is.
So this widescreen stuff, it's way too modern for apparently my driver stack. I wish it would help. Can I get some hints? Does anyone know xrandr? Outside and in, and especially with this widescreen thing? Minus R? What? That's rate. Yeah. It is listed, right? It is there. So how do we get it? Sorry? Out? Okay. Here we go. Thank you, sir. Well, a bit better. I don't know. Is that my fault? Is there something you can do magically about that? Sorry? It's nobody's fault. Okay, it's been like that before. Sorry? Does that ruin anything for you? The video angles? No? Okay, good. So let's do this. I'm sorry I'm late. So let's get started. I'm going to blast you with some USB stuff. I hope you'll enjoy it. I'm going to do a brief introduction. I'm going to talk about why I'm doing this talk. Then I'll talk about Universal Serial Bus, USB, some overview of the bus, background for the bus, terminology, a little bit about electrical specifications for the bus or properties of the bus, limitations of USB, communication, how we talk to each other on USB or using USB. I'm going to talk about descriptors. That's a really important concept in USB. Standard device classes, also pretty neat. Developing host software. We have these nice devices, but we also want software to talk to the devices, right? So I'm going to touch on different approaches to writing this software. Kernel drivers and user space drivers or applications driving the device. And I'll talk about libusb, a project that I've been involved with for a while and I like a lot. Some history of the project, kernel relationship for libusb as a user space library, and show you some code snippets. So my name is Peter Stige. I've been doing consulting in Sweden for a long time, software, hardware, security. I'm about to move here to Berlin. That's going to be a lot of fun to do some interesting cell phone research. I've been doing electronics and computing stuff since the 80s, and open source really passionately since about the 90s. Maybe you've heard me talk about coreboot some other time. I started looking at libusb in 2003 because I was doing a training session for engineers, marketing, executives, and one more group of people in the same seminar, and that didn't really work out so well. But anyway, I got into USB because I thought this is a really neat technology. So, and since this fall, I'm now the active maintainer of libusb. I'm also a member of the Swedish open source network FOSS-gruppen. So we're going to learn about USB, and this is nice because we want to use it in our own devices that we create and make. And sometimes we also want to write some software that can drive someone else's devices. How many have actually used libusb already? Right, that's nice. That's, I guess, about 30, 50 hands, something. Cool. So Universal Serial Bus. This is a standard managed by a company called the USB Implementers Forum Incorporated. They do this over at usb.org. And as far as standards development goes, I think this is a pretty, they make the outcome of their work really accessible. It's easy to just download the PDF. There's no click-through. There's no agreements. The PDF is just there on the website. It's really, really good. Standard covers a whole bunch of stuff. It's pretty detailed. Goes into specifics for cabling, for USB devices, connectors on devices and on hosts, and what connectors go where and so on. It talks about power consumption. It talks about the signaling that goes inside the cable and the communications protocol that goes on top of the signaling, and much more. The design goals for USB was to, as was mentioned in the introduction, be able to connect peripherals to PCs, because legacy ports were at the time about to go away, and there were good reasons for that. They were too big, they were sometimes kind of expensive, and there were too many different ports as well. So USB came in to take over the task of those random connectors on the backside of a PC. Plug and play was an important consideration when developing this standard. Mechanical connector keying is what helps with that. So it's not possible to insert a cable the wrong way, for example. If the cable fits, then you've plugged it in correctly. That's a simple way to make sure that things work easily. Of course, you can turn the connector upside down, right, and try to insert it, and it won't fit, and that's kind of annoying, but hey, they got a lot of things right, I think. A strong focus for USB, for the USB specification, was to allow devices to be very simple and also cheap to manufacture. And as a result of this, USB places a lot of responsibility on the host. And we'll talk a bit more, I'll talk a bit more about what the host is and what devices are in a bit, but it's, there's a lot of work to do as a host, and if you're a device, life is much, much easier. Communication is driven completely by the host. It's polled, so the host actually talks to each device in turn and asks it, do you want to do anything? And USB has become really, really popular, 8 billion host ports, and apparently it's increasing with lots of billions every year. A couple of connectors. The standard ones are the Type A and the Type B. On the top, I've heard that the big Type B on the top is being phased out, and that mini and micro should be used for new stuff. So the A connectors, they are supposed to be toward the host, and the B connectors are supposed to be toward the device. That's the rule. And yeah, I guess we've all seen the mini connectors. And on cell phones, I think in EU, you really need to have a micro USB connector if you're supposed to sell it. So important stuff, I've already mentioned host, that this is a big concept or an important part of USB. A couple of examples of hosts. The by far most common USB host is the one in your laptop or desktop computer, or server for that matter. It's a PC chipset, has a host built in. But there are also USB hosts in system on chips. So either if you're designing your own system on chip, I know that there's workshop and more about the Milky Mist that Sebastian has made, which has a USB host also, and it's also available in things like the OMAP system on chips, the processors, and larger microcontrollers as well. Device, that's everything you connect to a host. So mice, foam missile gun, printers, camera, memory card reader, etc., etc. Devices can be bus powered or self-powered, so they can devices can actually get all the power they need from the bus, which is a pretty nice feature of USB, but it's not really the only important feature of USB, in my opinion. Devices are self-describing. This is pretty important to get right. This is what device manufacturers can struggle a lot with, because if these descriptors, as they're called, that describe the device are not quite correct, then the operating systems are going to be upset, and the applications are going to be upset. They won't be able to communicate with this device. And nothing works until you get everything right. So if you're doing your own development, your own device development, like we'll do in the workshop later, then it can be a bit annoying because nothing works until you get everything right. But it's not that difficult if you're a little bit careful and you have the USB spec beside you when you're doing the work. So descriptors, there are a couple of different types of descriptors that make up the specification for the device. There's configurations, there are interfaces, and endpoints. And these have descriptors, each of them. I'll get back to that in a bit. And there are hubs. They are important. They help create more ports, because the host might only have a single port. However, you really want to connect more than one thing. So you use a hub as a splitter to get more ports. Some look at different versions of USB. Started out back in 96, 98, sometime with a USB 1, and low speed, 1.5 megabit, full speed, 12 megabit. Around this time, there was also a specification for the host controller interface. So the host controller is the actual chip, the PCI chip, or whatever bus it is on, that implements a host. And there were two standards, which was a little bit silly, but I guess the companies involved, they competed, and they each wanted their own. So there were two host controller interfaces, and this is a programming guide. It's a register specification for how you program a host chip. There were two, so you need two drivers in the kernel, or well, you only need the one that fits your hardware, but it's a little bit annoying that there are two to keep track of. So with USB 2.0, there was also the addition of high-speed communication, so 480 megabits per second. I guess this was because FireWire was doing 400 megabits per second, and well, anything new had to be a little bit faster, so 480 is what we got. And also around the time of USB 2.0, there was the EHCI host controller specification. So USB 2.0 host chips, they are all programmed exactly the same way. So we only need a single driver for that. That's nice, as long as they adhere to EHCI, that is. But most do, so that's good. And worth noting here is that while USB 2.0 adds high speed, a device can still be 2.0 compliant and compatible if it only does low speed or full speed. So saying that a device is USB 2 compatible, if a vendor does it or if I do it, then it doesn't really mean that the device is high speed or high speed capable. 2.0, after the base 2.0 spec, there was this on-the-go addition or supplement, which allows two devices to connect to each other. Take, for example, a digital camera and a printer. So if you have these two, it's kind of neat to be able to print directly from the camera, right? And this is what on-the-go would allow. It says host-free connections, but in practice, one of the devices will sort of switch personality and become a host for this particular connection. But it's restricted. It's not a full host in any way. Anyway, it's I don't know really how widespread it is. I haven't used it a lot. How many have used on the go ever? 1, 2, 3. Okay, yeah, 4. Cool. Did it work well? So. Okay. No, not really. Okay. Yeah, it's a neat idea, but maybe not that widespread. And a few years ago, there was USB 3.0, new specification and a new speed, of course, called super speed, and it's 5 gigabits per second. And along with that came also a new host controller interface, but it's still just one. That's good. There are some early devices out and some PCs which have USB 3, but I haven't used it much. And as far as the programming goes, it doesn't really change all that much either. In one particular transfer type, USB 3 adds a new field or a new channel identifier that you can use to further divide your communication into two streams or whatever. But overall, the communication is quite similar to what it was like before in USB 2 and also in USB 1. Electrically, the connections are point-to-point, so there's no on the cable level sort of splicing or cables just have to run from one port to another port, and it should be one A port and one B port. There are 4 wires in the cables. It's 5 volts and ground, and then there's differential signaling, so a data plus and a data minus. How many people know what differential signaling is and how it works? Cool? Excellent. So that's about 60%, I think. Quickly for the others, differential signaling means that you have 2 signals that do the opposite. Instead of having one static signal and another which is the value, you measure the value by seeing the difference in these 2 signals. And the bonus is that if there's some kind of interference on this cable, then the interference is going to be the same on both wires, and then you can effectively cancel it out. So, and it's the same principle also used in just plain Ethernet networking. There are some limitations to USB. You can only have 127 devices per bus, including hubs. So you can't go completely crazy, but 127 devices is still a lot. You can go maximum 7 levels deep. So the host is 1 level, your end device is 1 level, and the hubs in between also take 1 level. And you can have a maximum of 5 hubs, or active extension cables, which are also hubs. About cables can be a maximum of 5 meters. This means that the maximum distance, if you're using 5 meter cables, then the maximum distance you get is under 30 meters. So USB is not really meant for deployment of like a building-wide peripheral network, but rather some things that are pretty close to the PC or the host. And the current that can be drawn by devices is also limited by the specification. The absolute maximum is 500 milliamps in the base 2.0 spec. There's also been some additional specifications to allow specifically for charging batteries in handheld devices that allow the current draw to go up even higher. If the hub that the device is connected to is bus powered, then all you can get is 100 milliamps. So then you can do a lot less. And maybe maybe this device that you have needs a lot of power. It really needs more than 100 milliamps of current. Then it simply cannot work in that specific configuration if it is connected to a bus-powered hub. And the neat thing is that all this information about how much power that a device needs is also encoded in the descriptors. So the operating system can discover that, hey, you plugged in this device into a USB port, which can't really make it run at full capacity. So maybe you want to change that somehow. There's also a limit on how much current devices can draw in suspend, and that's only 0.5 milliampere, so not a lot. Communication, USB is a serial bus, as the name says. That means that only one thing happens at a time, even though there are these 100 odd devices. It's broken down into time slots. There's a concept of frames. That's minimum or the atom, communication atom on the wire. It's 1 millisecond for low speed and for full speed, and for high speed communication, it's 1/8 of a millisecond, so 125 microseconds, called a microframe there. Transfers is the logical unit or concept that is used for doing communication, for programming communication. So I say that I want to do one transfer, and this transfer is made up of a couple of different packet types which fit into frames. So I'm not going to go into a lot of detail about this. This is mostly relevant for maybe implementing a USB logic block, or implementing a piece of software that would bit bang a USB communication protocol. But it's more fun to focus on actually ready-made hardware that is already known to work, and just use USB for the data exchange. So that's what I'll do. I'm going to mention, though, the packet types, or the stages in a transfer. There's the first stage, which is a setup that contains information about what will this particular transfer be. Then there may be data, or there may be no data, and finally there's a handshake at the end. The handshake says yes. Well, the handshake is one of ACK, NACK, install, and ACK means okay, data transferred, fine. NACK basically is used to say no, I don't have any data yet. So the device responds back with a NACK, and that doesn't mean the communication failed. It means sorry, no data for you right now, come back later, please. And stall is, on the other hand, some kind of error that will need action to be corrected. I've been talking about transfers. There are 4 transfer types specified in USB, and understanding these and applying them to the problem at hand is maybe the bigger challenge in developing a USB device, because they have complementary but still sometimes conflicting properties, and it can be tricky, but with a few simple guidelines, it's easy to get it right. Control transfers is the most basic type, maybe easiest also. It's command response or request reply. I have some numbers here on how much bus bandwidth they are allowed to occupy. I have a lot of slides, so I'm going to skip over that, but you have the numbers here. Control transfers are tried to are delivered on best effort basis, so it might take a while before they actually go out, but they will never be lost. there's a limit on the data you can send as well. Interrupt transfers is periodical data exchange, and it can take up to 90% of the frame on the bus. So there's still 10% left, maybe for control, maybe for something else, depending on what software is actually wanting to communicate on the bus right now. Interrupt transfers are just one way. So control was request response, but interrupt transfers is always, an interrupt transfer is always just one way. Then there's bulk, which is just take as much bandwidth as you can, but there's no guarantee that it will arrive in any specific time. So it might take a while. Whereas with interrupt, it's periodical. If you set also in the descriptor that this is going to be transferred once per millisecond, then that is really the rule. It's going to happen. It's going to be allowed to do transfers and expected to do transfers every millisecond. Whereas bulk just takes as much as is free. When no one else is doing any kind of transfer, then bulk gets the rest. Bulk transfer is not allowed in low-speed devices, but is fine both in full speed and high speed. Finally, there's isochronous transfers, which you might recognize from FireWire also. This is guaranteed latency, so that's similar to the interrupt transfers, where the periodicity is really fixed. It will happen. There will be a transfer at this this given interval, and also the data rate is constant. So isochronous really reserves bandwidth on the bus for the particular data transfer. This is typically used for streaming. However, there are no retries. So if there's a signaling error on the bus, then all the other types, they're going to be retried, and eventually they will succeed, hopefully. But isochronous will just, it's like UDP, it's fire and forget, and if it arrives, then fine, but if it doesn't, then we're going to move on to the next stuff. So it's a good fit for real-time streaming. Endpoints, big important thing. This is what originates or receives all transfers, all data transfer to and from devices go over endpoints. Each endpoint has a number and a direction, 0 to 15, and in or out, not really complicated. One thing to keep in mind is that if you're going to do bidirectional communication, then you're going to need 2 endpoints. So, for example, with the interrupt transfers, as I said, they're only one direction. If you need interrupt transfers both going in and coming out, then you need 2 interrupt endpoints. They can have the same number as long as one is in and the other is out. And the numbers are really up to the device developer to choose the addresses. So, except for endpoint 0, which is the default endpoint, it's regulated in USB spec that this must always be a control endpoint, and it has a couple of particular requests or transfers that it needs to support. Read descriptor is one of them. But every other endpoint is really up to the device developer to decide, almost. So I'll come back to device classes, which can limit the developer somehow. So the question is, I mentioned 127 devices, and now I'm saying 0 to 15 addresses. There can be 127 devices, and each device can have a number of endpoints. And now we're looking at the endpoints and seeing that each endpoint within a device can have a number between, or will have a number between 0 and 15. And also the direction in or out. So a maximum total would be 16 times 2 in and out times 127 devices. Does that answer the question?
Yes, thank you.
So now we have a bunch of endpoints that are using a specific transfer type that fits our application, and we group them together and we specify some kind of behavior for them, and that is then called an interface. And for that interface, we make an interface descriptor also, and put some information there. Descriptors. There's an overall device descriptor. There's just one in each device. It has various information about the device, like the manufacturer ID and the supported spec number and so on. It's on the bottom. Inside is configuration descriptors. So one configuration or multiple configurations. Inside each configuration are interface descriptors, 0 or more. And inside each endpoint descriptor, inside each interface descriptor is 0 or more endpoint descriptors. So there can be multiple interfaces in each configuration. A configuration is a high-level mode for a device. I imagine it like one of these mode knobs that you can use for some devices, where the device completely changes its behavior, switching it back and forth. An example would be a guitar amplifier that I heard about, which can be either a storage device because it has an SD card reader, or it could be a human interface device because it has a display and a couple of buttons. Unfortunately, they were implemented as configurations rather than interfaces. So you have to switch between one, or you have to switch between the two. You can't have them both at the same time. Whereas if they had been implemented as interfaces in one configuration, then they could be running simultaneously. Interfaces are concurrent and independent. So again, multiple interfaces can be running and doing different things and offering completely different functionality within one configuration. I haven't seen a lot of devices with multiple configurations. Some advanced smartphones use it, for example, to switch the device into firmware upgrade mode. Other than that, not so much. So question is, are configurations and interfaces used, for example, with mobile broadband devices, which include the driver software on the device itself, and it shows up as either a modem or maybe both a modem and a device? And I'd say it depends on the manufacturer. The devices I have personal experience from is Huawei modems, 3G modems, and they do either or. They can only run in one mode. So they even complicate it further. They're not using either configurations or interfaces. They're using their own vendor-specific thing to switch personality of the device completely. So even though they could use these two configurations, they decided to make their device appear as only one thing at a time ever. When you first connect it, it's a CD, and if you send it some magic thing, then it's going to disappear. It's going to disconnect from USB and then switch something internally, and when it comes back, it's all of a sudden a modem. Does that answer your question? Yes. Thanks.
What I know the reason is because usually they're using cheap USB controllers that have only 8 endpoints. And so they can't use multiple configuration.
Could be limitations in the chipsets, definitely, yeah. Sorry? Okay. Apparently, some Huawei are both. Yeah. Maybe it's a newer model. The one I have is kind of old. While interfaces can be running at the same time and doing different things, configurations cannot. You can only select one of them. And also the configuration indicates how much power this device is going to need, or how much current it will want to draw in this particular configuration. And looking at the device descriptor, we'll get into the configuration descriptors and interface descriptors and endpoint descriptors in detail in the workshop. But looking at the device descriptor, it has, as I mentioned, the device version and the device class, which I'll come back to, and a vendor ID and a product ID to uniquely identify this device among all other USB devices in the system. There might also be some text stored inside the device as string descriptors, which are referenced from the device descriptor with the name of the manufacturer, and also configurations and interfaces can have names too. It's not used much. So this is a small diagram of the descriptors and how they relate to each other. One device descriptor, one or more configuration descriptors, and inside a configuration, one or more interfaces and endpoints within the interfaces. So device classes. There are some kind of devices that are really common. Keyboards, mass storage, memory sticks, modems, network connection devices, audio devices. These are examples of devices that when I plug it in, I expect it to work the same as the competitor's product, which really does the same thing, but maybe it has a green LED on top instead of a blue one. So this was also standardized by the USB implementers forum. There are a whole bunch of device class specifications. These are just some of them. So maybe human interface device is the most common one for keyboards and mice and joysticks and so on, buttons and displays. Mass storage class for hard drives, portable hard drives and flash memory sticks and so on. Communications device class has a serial port, Ethernet and more. Audio. And then there's device firmware upgrade, the DFU class, which is a little bit odd because, or a little bit different from the others because it interacts with other interfaces or other configurations. The DFU process, the firmware upgrade process, is a bit complicated, so it requires more from the host software. The benefit with having these device classes, they specify similar interfaces or identical interfaces so that a USB mouse will always look the same, or will at least be describing itself in a way that one single driver can understand. So I only need one driver to support all USB mice, which is neat and nice and great. Same thing for storage, of course, and audio and so on. Then there's the odd, or the exception, vendor-specific interfaces, and I really like these. Now, vendor-specific, that it's a lot of times it's really a bad thing. It's difficult to deal with and a hassle, and not really something you associate happy thoughts with. But for USB, I think it's actually awesome, because there are no endpoint restrictions on the device beyond endpoint 0, of course. All these device classes, they specify exactly which endpoints should be there and what should they do, what should they communicate, what are their limitations. Whereas a vendor-specific interface, you're completely free to make whatever combination of endpoints you want that happens to fit your application. So yeah, you make the optimal combination of endpoints, and maybe your device isn't really a HID, so then it's good to use vendor-specific instead. Another big benefit is that kernel drivers will not attach to a device with a vendor-specific interface, because the kernel drivers are written to support one specific device class, or maybe a couple of specific device classes. And for vendor-specific, there's no way to know what the device expects and how the driver should drive it. It's vendor-specific, so there's no kernel driver to have to consider if you're going to write some software to program this device on your own. This is important because unbinding a kernel driver from a device once it's sort of lodged on can be really, really painful. It depends a lot on the operating system. In Linux, it's fairly easy. You just have to have the right permissions, and then the driver is removed from this interface. But for Mac OS, you need super user privileges, and you need a reboot. That's not so nice. And then for Windows, you need to actually replace the driver that is attached to the device. So, and which also requires super user privilege, and which requires creating a restore point, which takes anywhere from a couple to 20 seconds. So vendor specific is good. It's often accessible without a specific kernel driver. This is true on the operating systems supported by libusb, except for Windows, which is always odd. And that's okay though, because on Windows, Microsoft has released WinUSB, and there's also this libusb 0.sys, which I'll come back to in a bit. Okay, so we've looked a bit at devices and how they communicate, and what about the situation of developing the host software? So the software, driving this device. We have a choice typically between implementing a driver in kernel or outside the kernel in user space. Now, a kernel device driver has many advantages, of course. It runs a bit faster, maybe avoids some scheduling, and it can use everything that the kernel offers, which can be a significant benefit for devices that should be tied into the kernel somehow. So I've written devices with existing infrastructure that's keyboard, storage, the speakers. All these already have interfaces in the kernel that we want to use. I mean, if I plug in a keyboard, a USB keyboard, and I start typing, I expect the characters to show up on my console, right? So there is some kind of console layer in the kernel that I want this USB device to feed into. Same with storage. I want to be able to mount my memory stick or the speakers. I want to be able to use my ordinary mixer software to control the volume of these speakers. The alternative is a user space application. Could be stuff like a cell phone firmware upgrader using the DFU, or really any application-specific devices. There's a lot of application-specific devices out there. One that came up on the libusb list a while ago was a color, what's it called? A color tuner that is used to measure color calibration. Is the word is used to measure the correctness of color representation or color on a flat screen. So there's not really a kernel API for that. There's no kernel infrastructure for that. So it makes a lot of sense to have such a device be vendor specific. And libusb. Libusb is a really straightforward API for doing USB transfers across a whole bunch of operating systems. Linux, Mac OS, we support Windows. Some versions of the API work on Solaris, and FreeBSD also has a libusb compatible API. Supports synchronous and asynchronous programming. Either you just fire and wait until the transfer is done, or you can queue up a lot of transfers and write your program in more of an asynchronous manner. And since version 1.0, libusb is also thread safe. Some history. This is a massive slide, but it's important because it's really easy to get confused by the couple of different libusb versions out there. The original libusb was version 0.1, started by Johannes Erdfeldt long ago, and it was just a helper API on top of the Linux API, the Linux user space API that the kernel already offered. libusb 0.1 was just a proof of concept, really, to test if this was a useful library. And apparently it was good enough because it got used quite widely. Maybe you've used a scanner in Linux or copied photos of your digital camera, sorry, or printed to a USB printer. And chances are that you might have, if you did this a while ago, you would probably be using libusb code. And this was only for Linux, and it got support for Mac OS also after a while. But Windows people, they also wanted this API because it's really pretty easy to use. However, that was implemented separately in the libusb Win32 project by Stefan Meyer. And it is the 0.1 API. It's just an implementation for Windows, and but it also extends the 0.1 API and adds support for missing stuff in original libusb. And to make this work on Windows, they also needed to come up with a kernel driver, which is this libusb 0.sys, which is really nice. And finally, since a couple of years, there's libusb 1.0. It was designed by a committee. We spent a lot of time on the mailing list going back and forth, and Sun created their open USB, which is basically their vision of libusb 1.0. But no one really stepped up to implement it until Daniel Drake came along and did a implementation, and he's also still the lead maintainer of libusb. The API was really thought through. While 0.1 was kind of proof of concept and try, is this a good idea? We tried to cover the basis with 1.0, and it seems to have worked out pretty good. There are still some things that have come up that we're missing, but that's for 1.1. 1.0 is much more complete. There's support for threaded, multi-threaded apps. There's isochronous, there's asynchronous API, etc., etc. And there's also the experimental Windows support since a while back. Using currently WinUSB, which I mentioned Microsoft has provided, WinUSB offers sort of the same functionality as the libusb 0 driver in theory, but in practice there are some differences. We also want, but so far WinUSB is what we can make use of in libusb on Windows. libusb 0.sys we really want to support that because it allows an easy migration from libusb Win32 into using libusb 1.0 on Windows, and it's a ticket for it. There hasn't been a release of libusb 1.0 in a while, and I'm working to make sure that we get that release out really soon now. And the goal is to have it out before the end of the year. I think that's going to work out. Yeah, you laugh, but no, I'm pretty sure that'll be fine. So the libusb kernel relationship, there's always a kernel driver, right? I'm standing here and talking about how to use libusb to program devices from user space, but we can't do that directly ever. We always have to use a kernel driver somehow, and we in libusb rely on a kernel driver which provides some kind of API that we can make use of and go through to reach the devices. Linux has USBFS. It was called USBDevFS before. On Windows, there's this WinUSB and libusb drivers that I mentioned, where WinUSB, it's from Microsoft, it's included in Vista and later, but it's also possible to install after the fact on older systems, so XP, and they made some DLL package that you can redistribute also very easily to add WinUSB to a system. Also check out libwdi, which is also mentioned on the libusb.org page if you want to do this this driver control, driver installation stuff on Windows. Really nice library for that. And libusb 0.sys is the kernel driver from the libusb Win32 project, which is still very much relevant because a question?
Yes. So is WinUSB an effective way to work around the vendor and device identifier registration process, sort of? Whereas it,
On
if you have
Windows,
a-
you mean?
if you have a device that has a like a new identifier or identifier that isn't registered for the well-known classes, like a
Keyboard.
so that would work without having to add the device, the vendor and device ID to the system. Okay, cool. Thank you.
Well, a keyboard is picked up by the head driver. So if it's not something that the system will identify, then is this question specific for Windows? Yeah. Okay. So the question is, if I understand you correctly, can libusb sort of skip the requirement to have this tie a vendor ID, product ID to some kind of specific device class in Windows? And the answer is no, we cannot. Windows needs to have a driver for every device that it has attached. It needs to have a device class for every driver. But there are some tools to automate it, and libwdi is able to do it automatically. There are also some helper tools to create the init files and necessary stuff to do that installation.
The follow-up question is, or the original question I asked, because for the registration you need administrative privileges to add the information to the system.
Yes.
Whereas if it was possible, you could just plug in a device without having administrative rights and get it to work.
So yeah, if it's an unknown device to the Windows system and you want to program it, then there needs to be a driver installed and you need admin privileges, and there will be a restore point created. However, you can automate it, all of it, using libwdi, so that the user just gets this administrative security confirmation dialog, clicks yes, and then everything happens automatically. But yes, it will need the user's consent or acknowledgement or approval to actually do the installation. There's no way around that in Windows. With with WinUSB or with libusb 0 driver. So the libusb 0.sys driver is nicer because it allows full access to the device, whereas the WinUSB driver, it only really supports interrupt and bulk transfers and control. It doesn't support asynchronous. Too bad. The libusb 0.sys driver has been also signed, sponsored by the community. Some code, libusb. This is how you find a particular device using libusb 1.0, the 1.0 API. It's not too bad. You need a device handle, and you call, for example, open device with a vidpid, and you give it the magic vendor ID, product ID, and maybe you get an error, or maybe it works. This is the code for a control transfer. Also not too bad. Forgive my terse variable names. Device handle is the one we got from Discovery. Vendrick is saying that this transfer is a vendor-specific request that is going to be addressed at the device instead of at the interface or at a specific endpoint. The REQ parameter, the request parameter, is just an arbitrary number that I send to the firmware. Val is also arbitrary value I send to the firmware. 0 is index, another arbitrary value. Data points to, or the data buffer is some data bytes that I want to send, and len is the number of that, and 1000 is a timeout. Pretty straightforward. Here's some code for interrupt transfers. It's a little bit longer. We do an interrupt transfer. In this case, I want to ignore timeouts because I want it to spin over and over and read data as long as possible. And some error checking, and finally down the bottom there's some processing of the input. I want to say thanks to the Chaos Angles, as always, because this is a great conference. And I want to say thanks to all the libusb contributors over the years. So some of the names are Johannes Edfeldt and Daniel Drake, but there's also a lot of work done by Xiaofan Chen and Tim Roberts, Nathan Jelm, and Pete Battard, or Neiman, and other guys as well. Yep. So if there's one thing you take away, please remember that USB is much more than a serial port with power. If you want to do a workshop on creating a USB device, it's going to be tomorrow at 10 p.m. in the big workshop room, which may be B04 or maybe A03. I'm sorry, I don't know the exact room number. And I guess we've run out of time for questions, so come talk to me if you want to ask anything. Thanks.